Welcome to the Ashby Village Science and Ideas Group. I'm Joe Evinger, and I coordinate this group's events with the help of our co-host and tech expert, Hilary Naylor. All of our members here have educational and work experience backgrounds, quite varied, but we all share a common interest in science and new ideas. We currently have over 70 members in our Science and Ideas group and another 100 on our guest list. We meet via Zoom the second Thursday of each month from 3 o'clock until about 4:30. We have a different guest speaker each month who speaks to us on a topic related to science and ideas. For instance, next month we'll have Smithsonian curator Matt Schindel will speak to us about his new book, For the Love of Mars, A Human History of the Red Planet. We invite all Ashby members to join our group. Others interested in Ashby Village and our presentations are also welcome. One quick commercial. Ashby Village is a 501c3 tax-exempt nonprofit organization. I ask Hillary please to place a link to our village website in the chat. And to our guests, please consider a donation to Ashby Village or even joining our organization via our website. Onward. Sarah Evinger will now introduce today's speaker, Noah Finnegan.
We're really happy today to welcome Noah Finnegan, who is a professor of Earth and Planetary Sciences at UCSC, specializing in geomorphology, the study of erosion, and how it shapes topography. Noah teaches classes focused on geomorphology, active tectonics, and hydrology. Since starting at UCSC in 2009, Noah's research has focused mainly on processes of erosion and sediment transport in rivers, and more recently on the mechanics and hydrology of landslides. Before moving to California, Noah had always lived in locations in the US that were covered by glaciers during the last ice age. Welcome, Noah.
Noah. Thank you. Which is why California still looks sort of strange to me, despite having lived here for a long time. Okay, I'm going to go ahead and share my screen and get started. Okay, let's see here. Okay. How does that look to everyone?
Looks good.
Looks good. Okay, I'm going to get started. Well, first off, thank you for having me here to give this talk today. It's a real pleasure to speak to this audience. I really welcome the opportunity to kind of get outside of my normal cohort of people and talk to people in the public. So this is really a nice treat for me. So what I would like to talk to you today about is some of my research on landslides, but kind of more generally about landslides in California, which you've probably heard a fair amount in the news about lately. So the title of the talk is Moving Mountains, Slow Landslides in California, Where, Why, When? And let's just dive right in. Okay, so why study landslides? Globally, in terms of loss of life, they're a more significant factor than hurricanes and wildfires combined. From an infrastructure perspective in the US, many billions of dollars a year are spent mitigating and repairing damage from landslides. This number is something like $20 billion per year globally. And what's kind of interesting about the science of landslides in particular, as nicely articulated in a recent piece in Scientific American, is that, well, we know they kill and hurt thousands. Science, to some extent, ignores these disasters from a funding perspective. And there's reasons for that that are kind of beyond the scope of this talk. But I'd just like to put that out here right at the beginning and just to emphasize that, compared to other natural disasters, there is actually very modest funding of science on landslides in this country. And hopefully this talk can show you some of the scientific directions that we're taking to try to get on top of this hazard, but also just show you why it's an interesting topic. Okay. As many of you likely know, California has substantial landslide problems. In the news over the last few years, I think, are the Big Sur Coast, Highway 1, Caltrans, the state agency that maintains our roads, has really been engaged in kind of this incredible battle to try to maintain Highway 1 on that section of coastline. And for much of the last 5 years, sections of that road have been closed, almost always due to landslides of one kind or another. The other place that you probably have read about or heard about recently is Rancho Palos Verdes in LA County, where there's a huge subdivision that's kind of sliding into the ocean right now. And these are the two hotspots at the moment in the state, but there are many others at many different times. So to begin, let's just do some definitions. What is a landslide? A landslide is a process that results in the downward and outward movement of slope-forming materials, including rock, soil, artificial fill, or a combination of these. And the materials may move by falling, toppling, sliding, spreading, or flowing. And that's the definition from the U.S. Geological Survey. I'm a lumper more than a splitter scientifically. So for me, I think the kind of key aspects of landslide classification are what's involved in the failure. Is it just soil, that kind of veneer of organic material and disaggregated minerals that exist just at the very surface of the earth? Or does it involve the bedrock at the surface of the earth? And that's an important distinction. And then how fast is it? Is it something that is a catastrophic event, or is it something that's creeping almost imperceptibly? And in this talk today, I'm going to focus on slow-moving bedrock landslides, sometimes known as deep-seated landslides. And there's at least two good reasons for that, to do that. Number one, these slow-moving, deep-seated landslides are ubiquitous in California and represent a chronic source of infrastructure damage. At the same time, from a hazard perspective, understanding why some landslides move slowly helps us to understand better what controls where and why catastrophic landslides occur. And I'll just note that for faults, the exact same issue exists. In California, we have some faults that are creeping all the time, such as the Hayward Fault in your guys' backyard. And there are other faults like the San Andreas that are, well, the San Andreas up where we are, which is locked and periodically fails in these catastrophic events. And so what governs that type of frictional behavior is something that we don't understand that well, and which cuts across many different geophysical fields, including landslides and fault mechanics. And I would just also know that the Berkeley Hills are well known for active slow landslides. So here's a map from an engineering report of the Berkeley Hills. This road right here, this red one is Marin Avenue, just to sort of reference. There's Summit Reservoir up here. The red ones are known active landslides, and these were here when the infrastructure was built, and so they're a known source of difficulty in the Berkeley Hills. You'll see headlines often related to this. Here's one from SF Gate. When property lines run through the front door, the slowly shifting ground in the Berkeley Hills area means the land that's yours today may be your neighbor's tomorrow. And this is an interesting legal digression, which I wanted to spend a second on, which is that we do have laws governing the land moving and what we do about property boundaries. But these laws were mainly conceived for earthquakes, and specifically after the 1964 Alaska earthquake, some codes in California, Alaska were adapted to allow property boundaries to move with the earth during earthquakes. But landslides are treated differently. And so as a recent case in Palos Verdes attests to, courts have found that property boundaries are not necessarily going to be redrawn when you specifically have slow landslides. So courts are seeming to make a distinction between catastrophic and slow motion. And what that means at a practical level is that someone's house can move onto your property and then you can sue them for trespassing on your property. And there are litigations in Berkeley and certainly now in Rancho Palos Verdes on this very point. So it's kind of touches on some legal issues as well. Okay, so quick physics. Landslide materials, particularly those that are unconsolidated, are granular in nature. If the ground is saturated, the pockets between the grains are water filled, as we can see in this. So this is sort of a schematic close-up of this landslide here, which is in Ventura County. So the water pressure within the pore spaces in soil or rock acts to counter the forces that exist between particles. And it's these contact forces that create friction, right? And so macroscopically, what we experience as friction at the surface is really related to kind of grains of sand grinding into one another. And that water pressure tends to push out against those forces are acting between grains. And so in a sense can be thought of as resisting friction or counteracts friction. And friction is a thing that resists sliding on hill slopes. The link between water pressure and rainfall then is why landslides are a wintertime problem in California. We get a lot of water infiltrating into the ground that changes the pressure in the ground, which in turn changes friction. So I've divided my talk up into 3 pieces: where, when, why. Let's start with the where. This is a map. Well, let me just state that active slow landslides in California are largely confined to one geologic formation. It's something that we call the Franciscan Melange. So if you take the geologic map of California and you just look at the places where we find this one rock formation called the Franciscan Melange, this map here on the left is showing you where that outcrops in the state in green here. What's shown on the right is our best estimate of where active, slow-moving landslides exist in the state of California. And this is as mapped from radar measurements that are made from satellites. And so it's the best way that we kind of have to look synoptically over the whole state and get a sense for where the ground is moving and at what rate. And I think what you can see immediately from comparing the map on the left and on the right is that there's an incredible spatial correspondence between where we see the ground moving all the time and where this one particular rock formation outcrops in the state. So that really leads us to a deeper exploration of what it is about this particular rock formation in the state that leads to this propensity for failure. And I would just say, if you look at the California Geological Survey produces maps of landslide susceptibility, you can see that the susceptibility to landsliding, deep-seated landsliding in this case, which is shown in this map on the left, is largely driven by where the location of this one rock type outcrops in the state. The topography in the Sierra Nevada is much more impressive than it is in the Coast Range, but you don't see a lot of landslide susceptibility there because the rocks are quite strong, which is what allows us to get such spectacular topography there to begin with. So to have an understanding of like what it is about this particular rock formation in California, we need to go back in time. And we're going to go back in time, in this case, 80 million years, into deep geologic time, and think about the sort of plate tectonic history of California. And in particular, California used to have a subduction zone, which is the type of plate boundary where one plate is sliding underneath another plate, much like we have in Cascadia, Oregon, and Washington today. And the formation of the current plate boundary, which is defined by the San Andreas Fault, is actually a relatively recent event, geologically speaking. So this is an animation I'm going to show you from a woman named Tanya Atwater, who's a very famous professor at UC Santa Barbara, who is really the first scientist to kind of understand how California fit into the new plate tectonic theory that came about in the 1960s. So what we're seeing here is present day California, and we're seeing that plate, which was called the Farallon plate, sliding beneath what is now California. And when this thing, which is a mid-ocean spreading ridge, contacts the coast of California, the San Andreas Fault is born, and we get to our sort of present day situation where the plate boundary is now defined by the San Andreas Fault, but until very recently was defined by one plate sliding underneath another plate. Okay, let's see if I can get to the next. Okay, so if we were to zoom in on one location along the sort of the coast of California in the distant past, we would see that Farallon plate diving beneath what is now the Central Valley and producing volcanoes in what is now the Sierra Nevada, associated with the melt of that plate and the release of water into the crust. Okay, so the Franciscan Melange in this view is then the stuff that's kind of being scraped off of that downgoing Farallon plate and actually being accreted to the North American continent. And that's the environment that that particular rock formation was formed in. And until we understood about plate tectonics, we didn't really have a good model to explain the existence of this Franciscan Melange, which has been recognized since geologists first started mapping California, but whose origin was sort of unclear until we had this perspective that was provided by plate tectonics. And Tanya Atwater is really the person who first put this all together in a coherent way. So when we see these green rocks outcropping along the coast of California that are hosting landslides, that really is show that's rocks who formed in this deep subduction zone, which has now been uplifted and exhumed in the California Coast Ranges. So that's the what, or that's the where, I should say. And as the name implies, the Franciscan melange is a chaotic mixture of mainly clay-rich sediments that came from an ancient ocean and that were scraped off of that ancient subducting Farallon plate. And kind of one of the key features of this particular rock type is that it has this sort of mushy clay-rich matrix that's filled with blocks of much harder rocks, cherts and sandstones. And those sort of are floating in that clay. So here's an example from the Sonoma coast of the Franciscan melange, and this is typically what you will often see. It's sort of hard bits. It's like plum pudding. There's lots of different food analogies that people will use, chocolate chip cookie dough, that kind of thing. So that's the where. Okay, so then let's talk about the why. Well, Franciscan melange landscapes have a really distinctive feel or even a distinctive vibe. And I use that word just because you have to represent, UC Santa Cruz. And that vibe really comes about due to the absence of trees and the scattering of boulders of all sizes and types and the hummocky topography. This is an example from the field site that I've been working at for about 8 years in Santa Clara County. But if your experience, you may think Marin County, Sonoma Coast, the Diablo Range, the Eel River Canyon, these are all landscapes that are formed on top of this particular rock formation and all share many qualities in common and which provide us with some insight into why this rock unit in the state of California behaves so uniquely. Okay, so I'm going to summarize some work by a recent PhD student named Jesse Ham, who worked at UC Berkeley under the geomorphologist at Berkeley. His name is Bill Dietrich. And Jesse is now a professor at Simon Fraser University in Vancouver, Canada. Would be a great person to have on, by the way, if you're interested, if you're looking for speakers, he'd be really good. So Jesse did his PhD in part on understanding the unique hydrogeology of the Franciscan melange. And our way into thinking about this is the noting that these melange landscapes typically have no trees. This is a really defining characteristic of the melange that's apparent even from space. So what's shown on the left is a satellite image of Northern California. The South Fork and main stem of the Eel Rivers are shown there. And that black line here is dividing the Franciscan melange, which is east of that line, from a different rock formation, which is not the Franciscan melange. And kind of the key thing to note here is that you can see that the trees, which are ubiquitous on the coastline here, this is kind of Mendocino, Humboldt County, stop as soon as you get to that mapped boundary between these two different rock types, which are, one is called the coastal belt of the Franciscan assemblage, and this is the central belt, which is the melange, which is what's in red. If you were to zoom in on the ground and you were to be the west of that boundary, you would see a landscape that may be familiar to many people that have been in Mendocino County, thick Douglas fir and redwood forests that are full of trees. And if you were to go to the east of this boundary, you would see a landscape that looked more like what is shown in the lower image here, which is one that's largely devoid of trees and which is pockmarked with rocks sticking up through the landscape here and there. What's crucial to note here is that both of these landscapes receive exactly the same amount of rainfall, about 2 meters per year. So this is not a vegetation signal that's being driven by water at all. It's something to do with the rocks themselves. And what Jesse discovered in his PhD was that this melange has incredibly low permeability. And permeability is the capacity of a porous material to transmit water or any fluid. What that means is that the plants that grow on this landscape can't access the water that's held in its pores. And even in steep topography, the groundwater does not drain out of the landscape. So in a sense, this is akin to shale gas, which is why fracking was first developed, is that we knew that there were these rock formations that held huge amounts of natural gas in them, but the rocks didn't have the permeability to extract the gas out of those. And we developed through a lot of money and research this process called fracking, which is very controversial, to actually basically create permeability to get gas out of the ground. Well, this is a landscape where we're talking about water, not gas, but it's the same idea, is that there's a huge amount of water in the landscape, but it's so tightly bound up in these clay-rich rocks that the plants aren't able to get the water out of the ground. And hence, except for a few oak trees here and there, there's very little that grows other than the invasive European grasses, which came in at the time of ranching. So if you were to look at wells that are drilled in the Franciscan Melange, you'll find that the water table is almost always very close to the surface. And this is really distinct from other places geologically in the state. So here are two figures from Jesse's work at the left showing you two different wells, one in that upper landscape in blue and one in the lower landscape in red, showing you the position of the water table below the surface throughout a year in that upper panel here. And what you can see is that in that lower landscape, despite the fact that there's no vegetation, the water is almost always right at the surface. Whereas in that landscape at the top, which is in blue, the water table is tens of meters below the surface, and it's the trees have roots that extend deeply into the ground to get to that water. So the fact that the water table is always near the surface means that you sort of have perennially high water pressure in this particular rock formation. And it's that in combination with the very weak nature of the rocks themselves that lead to it behaving in a manner on at least geologic timescales that we sometimes sort of compare to melting ice cream. Indeed, we kind of refer to the topography of the Franciscan Melange as melting ice cream topography. It has a sort of, and so this is sort of a characteristic in the lower left here of what the sort of topography looks like in the Eel River Canyon. And at right here is the landslide that I've been working on for 8 years now, which is just a little bit south and east of you guys, Oak Ridge earth flow, which is very close to Calaveras Reservoir in east of Milpitas. Okay, so that's the why. So hopefully at this point, I'm going to look at my phone and see we're doing okay on time. So the where involves understanding the plate tectonic history of California. The why involves understanding something about the hydrology of this particular rock formation. And so then the when is really starting to focus in on questions that are more pragmatic in nature and related to sort of management and hazard mitigation. So this is a plot showing you the motion of a bunch of different landslides in Mendocino, Humboldt, California, as measured from a satellite. And these are 5 years of data showing you rainfall at the bottom and velocity of these landslides moving down slope. And what you can see is all these landslides go through these seasonal cycles where in the winter, when it rains, they accelerate and start moving more quickly. And in the summer, they slow down and move often imperceptibly. So because of the linkage between water pressure and landslide motion, the seasonality of rainfall in California is really a key control on landsliding. But as scientists, we can and should get a little more specific than this. And specifically, kind of two questions that have motivated my research and which we can ask we can ask in a more specific way that will be more useful from a management and mitigation perspective. And those questions are, number one, what controls the timing of the onset of seasonal deformation for California's slow-moving landslides? When do they turn on? And how, with an understanding of rainfall and when it's being delivered to the ground and at what rate, can we make a prediction about when landslides will turn on? This is a very practical question. Number two, what is the relationship between how much winter rainfall occurs and how much landslide motion occurs? Again, on some level, this is the basic question that we're always concerned with when we're thinking about these kinds of slope hazards. And these are sort of two questions which I'm going to try to tackle in the last part of this talk. And to tackle these questions, I have developed a long-range landslide monitoring site at this particular landslide that's called Oak Ridge Earth Flow. It's located just to the south and east of you guys, back in the hills behind kind of Fremont and Milpitas, very close to Calaveras Reservoir, which is the main reservoir, the biggest reservoir that San Francisco Water Utility operates outside of Hetch Hetchy in the Sierras. It's located in a band of Franciscan Melange that's in the Diablo Range. A bunch of my graduate students over the years have helped build out a huge network of monitoring infrastructure that we have that includes permanent GPS stations to measure the motion of landslide, strain gauges that are looking at the displacement of the landslide at much finer temporal and spatial resolution, and a network of wells that we have punched into this landslide that can give us a sense for what the plumbing is like, what the water pressure is doing. And, you know, to kind of frame this question of what controls the timing of the onset of seasonal deformation, I'm going to show you data from a single GPS station, which is located where this blue dot is, right in the middle of this slow-moving landslide that I've been studying, We're looking at displacement. So this is just motion of that GPS station downhill over time. And this is this last year. And what I'm showing is fall of 2023. This is hourly rainfall that we measure with a rain gauge at this site. And what you can see is that in the fall of 2023, there was a bunch of rain and there was no motion of that landslide until one day early in February of 2024, the landslide came to life and started moving. And by, I guess, what is that? By June of 2024 had moved about 1/3 of a meter downhill. And 1/3 of a meter is not a big deal from the perspective of, a catastrophic landslide. But if you have a road or a gas pipeline, a 30 centimeter displacement is a big deal. And this is why, there's a lot of focus on these types of features. Okay, so what is it about this moment that is important? What happened here, and what happened such that all this rainfall did nothing, and then all of a sudden we crossed some apparent threshold, and this landslide came to life? Well, we can make some observations based on years of monitoring. And so this is a figure that just shows rainfall on the upper plot, bar graphs of just how much rain fell every day starting in 2015. And this is, again, the field site that I've been maintaining at that site that I just showed you. This is water pressure within the ground in response to that rainfall. And this is the lower panel is the velocity of the landslide. And what I really want to call your attention to is that in most years, we see that the landslides begin moving after something like 20 to 30 centimeters of rainfall has fallen on the landscape. And we see that there's a sudden water pressure rise that occurs something like 1 to 2 days, that occurs over a couple of days and often accounts for most of the change in water pressure that we see throughout the year. So I'll call your attention to 2017 in that middle plot where we can see the water pressure jump up about 20 kilopascals in a couple of days. And 20 kilopascals is the equivalent of about 2 meters depth of water. So it's the water pressure that's produced by about 6 feet of water. That's much more water that can be delivered in a single rain event. And so it really begs the question of what's happening here. How is it that nothing can happen for weeks and weeks and weeks, and then all of a sudden we release a huge amount of water and the pressure goes up and landslide begins moving? Well, the best way I can kind of explain this is through sort of a common experience that many of us has had. Is I have a dry sponge here and I'm going to pour water on that. And you can think of this dry sponge in some ways as analogous to California at the end of the summer, right? The landscape is parched. It hasn't rained in 6 months. And the ground is incredibly dry. And when we start raining in the fall, let's imagine this is a landslide, and I'm not going to move until there's water pressure at the base of this sponge that lowers the friction and enables me to move. But the landscape in California at the end of the summer is behaving like a sponge, and in particular is able to hold a huge amount of water against gravity because of the surface tension of the water. And this is one of the kind of interesting properties of water. So making an analogy from our sponge to a landslide, the landslide can absorb a huge amount of water before we actually see a pressure response at depth, which we're finally getting here. So the kind of key lesson from the sponge is that the ability of the sponge, or by making an analogy to soil, to hold water against gravity means that there is a long delay between when it starts raining and when rainfall is felt in the ground as a change in water pressure. And while this is relevant in my case to landslides, this is also very, very relevant for understanding in general how water moves through our environment in California. So it's also relevant for water resources and for flood prediction. Storms at the beginning of the winter behave very, very differently hydrologically than storms at the end of the winter. And the main reason for that is due to the effects of the antecedent moisture in the ground. Okay. So then I will spare you the gory details of this, but I will suffice to say that using math, we can then take this understanding and predict the timing of landslide motion in terms of kind of 3 things that are relatively easy to measure. How dry is the sponge at the end of the summer? What what is the rate at which water is being absorbed by the sponge, which is mainly rainfall, and how much water leaks out of the sponge between rainfall events. And kind of taking those three pieces together, we can make a sort of quantitative prediction about when landslide motion will occur within this Franciscan melange, which has very unique hydrology, but which hosts most of the landslides in the state that are slow moving. And this is an example of a recent publication that my group put out that sort of that put forth this sort of approach to trying to predict the onset of landslide motion in California. Okay, so for the last few minutes of the talk then, I just want to shift gears and talk about this second question, which is one that many engineers are concerned with, which is what is the relationship between how much winter rainfall occurs and how much landslide motion occurs? Here's a plot produced by one of my former graduate students showing you water pressure measured within the ground at our landslide site and the motion, the daily downslope motion of a GPS antenna. And what you see there is there's this really nice relationship here between water pressure such that basically you require some threshold of pressure to get the landslide moving. But just like the sponge, when the ground is saturated, and so I should just, let me go back one slide here. Our observations, such as this one here, tell us that to have substantial movement, water pressure must remain high within the landslide, right? If our landslide is going to move, we need to be kind of in this regime where the water is constantly at high pressures. But like the sponge, when the ground is saturated in the winter, the water leaks out very, very efficiently. And we see this at our landslide site in the form of abundant springs all over the landslide. And the springs whose discharge we can measure is intimately connected to the water pressure that we can measure within the ground, right? So in a sense, this analogy to the sponge works really well. And when there's a lot of water in the sponge, the water leaks out really effectively, which just means that there's a real premium on keeping water pressure high through input of rainfall frequently in order to have landslide motion continue at high rates and to accrue lots of damage. And so it's really only winters like the last two that we've experienced where we get that kind of sustained input of water, where we get a lot of motion on landslides. So wet winters with sequences of large winter rainfall events, often these atmospheric river events that you guys have probably read a lot about, are what keep water pressures elevated for sufficiently long periods of time to allow for substantial movement and therefore substantial damage and therefore attention in the media. Dry winters may never see water pressure sufficient to trigger motion, at least down where we live. Up further north in Mendocino, Humboldt County, where there's much, much more rainfall, their landslides are a bit less sensitive to winter rainfall because they just get so much more than we do. So I will just say again, I'm going to show you some data from our field site. This is displacement measured since 2016 on a GPS station. This is velocity of that same GPS station, the middle panel. And then finally, this is lower panel is the water pressure measured at one location within this landslide. And what I hope you can see is that drought year that preceded the previous two winters, the few winters of drought that we had prior to the last two winters, never really raised water pressures enough within the landslide to cause measurable motion, right? And so the sort of motion of these landslides is really intimately connected to how much and when the water is delivered during California's winters. And in Central California, where we are, the water amounts that we get during the winter are variable enough that in some years things happen and in other years they don't. And I'll just leave you with one last thing from a recent paper, which is that we've recently been able to use models of friction that are developed for earthquake faults to actually predict the relationship between water pressure and landslide motion that we measure. So here's an example of two landslide sites where we have constraints on the water pressure at the base of the landslides, and we can measure the velocity of the landslide. And the red line is just showing you a prediction of motion that comes from a frictional model that's developed to understand earthquake faults, and which here is showing us that our understanding that's used for understanding earthquakes can also do a really great job of helping us understand landslides. And the last point I'll just leave you with is sort of what's next is climate change in California, especially in Central California, will probably change the distribution of rainfall. It's probably not going to change the overall amount of rainfall we receive as much as it will change how that rainfall is distributed over the year. And in particular, so-called whiplash events, where extremely wet years follow extremely dry years, will become more prevalent. And how this change in the way that rainfall is delivered in the state will impact landslide hazards is an open question that many, including people in my group, are tackling right now. And I'll just leave you with 3 images of my field site, which since 2016 has experienced the second wettest winter on record in California, and one of the driest, and a huge fire that burned our entire field site. And so really over the 8 years that I've been working in this site, we've seen an immense amount of variability. And it's that variability that we want to be able to translate into some predictive understanding. So I will stop there, and I'd be delighted if there are any questions.
Okay, can I ask anybody if they want to either raise their hand? Hillary will run the show here. Sarah?
Hi, thanks so much. I actually understood almost every word you used. It was really exciting. I was curious about what are there state agencies that benefit from your research on a regular basis? CAL FIRE, East Bay Mud, other groups.
Yeah, I mean, for me, I have recently, Caltrans would be the most obvious one because they're
Okay.
in sort of constant, and I have been talking to the lead engineer who's working down on Highway 1 in Big Sur about some of this stuff. But they're constantly in a reactive mode, understandably. So some
Yeah.
of the ways that we think about this, they don't really have the luxury to think in this way because they're sort of like called in when the road falls into the ocean. And at that point,
Yeah.
it's a different problem.
Yeah.
So in addition, the San Francisco Water Utility, whose land I operate, whose land that landslide exists on, I often will chat with them because I have a pretty intimate understanding of the hydrology there now, which is something they care a lot about.
Yeah. Thanks.
Looks like Roger has a question.
Yeah, okay, so I just wanted to ask, I think our experience with these sort of mudslides, landslides, is the sort of catastrophic thing that happens in the winter associated with a lot of rainfall. Now, I think what makes the headlines is probably a different motion than what you're looking at. And I wondered how much of that effect can we ascribe to the sort of the catastrophic amount of rainfall that comes. I'm thinking about these atmospheric rivers that seem to have become more prevalent recently. And last year, I think it was that we didn't get very much rain except for these big rivers that came in, and then we would get a huge amount all at once. And so does a distribution of how much rainfall, if it's a long, slow process or a huge amount of rainfall all at once, does that make any difference?
Yeah, it's a really good, very insightful question, which there's a lot in there. So what I will say is the manner in which the rainfall is delivered is hugely important. And so first, your question about slow versus catastrophic failure. Some landslides transition from the one to the other. What governs which of those two things happens is not something we understand well, but is something that's kind of at the center of my research right now, is trying to understand what does that. So we don't have a good answer for that, but we know that certain materials are more prone to catastrophic failure versus others. As far as thinking about how rainfall gets delivered, first of all, atmospheric rivers, landslides happen disproportionately in atmospheric river events. So that's because we can get rain rates up. But I think of the landslide problem as sort of like landslides are boxes of different sizes on the landscape, and they fill up over different time intervals. So some small landslides, especially the ones that are restricted to the soil, they can respond to a single storm event. They can respond to 15 minutes of incredibly intense rainfall because you can often saturate the soil in that period of time. Whereas a landslide that's extremely deep may be sensitive to variability on months or even years. And so the answer to your question is it really depends on the details of the size, the scale of the slide in question, and the hydrology. And but I think what you're getting at really is why this is both an interesting problem to work on, but also one that's pretty vexing, because you need to know a lot in order to have that understanding. We've been able to generalize for one rock formation in California, but it's really just one.
Okay, thank you.
I have a question. You've talked a lot about water and rain and how it affects a landslide. Does climate and temperature have much to do with it? I'm imagining an area with very low permeability, so there's a lot of water very near the surface. If it gets very cold, there's going to be some ice forming, at least in the top inch or two. That's going to cause pressure, and I'm envisioning back that slide you showed with water in between the different pieces of rock and soil. How big a deal is that in effect?
Yeah, it's a good question. I mean, most of the landslides we think about are deep enough that they don't care that much about temperature variability like you're talking about, right? Because the sort of the depth at which daily variability in temperature penetrates is just a few tens of centimeters. So most of the things we think about aren't probably directly affected by temperature. That said, to the extent that you're messing with plants at the surface, plants are a way that you can couple the surface to the depth, because roots often are quite deep. And so I will say, we know that fires radically change hydrology in several important ways. And so I would say fires are an example of where extreme temperature has a pretty profound effect on landslide processes, especially within the soil. And that's induced by changes in the nature of the hydrology. But that's a sort of special case. In most other cases, we don't worry so much about the temperature variability at the surface.
It looks like Mark has a question.
Yeah.
I have a question. Is the insurance industry at all interested in slow-moving landslides?
That's a good question. I mean, I think, it's the standard disclosures that you have to, the standard sort of property disclosures, there is a thing about landslides. And so, you'll have to hire somebody to look at what we know about where landslides are. And before you can insure a house and get a mortgage, someone's going to check, right? Now, how well we know that information is a separate question. But I think in California, at the moment, landslides are really minor in comparison to fire, which is a thing that's really shaking up the state insurance industry much more at the moment.
Sally's raised her
I
hand.
have a question. I used to live in Pacific Palisades, and the landslides that threatened Pacific Coast Highway, I was told, were due to the fact that the cliffs were basically composed of tabby, which is oyster shell, and therefore very slippery and does not adhere to itself well. And I wanted you to comment on that. How much is that precipitated by rainfall, or does it matter that much there?
It's both. I mean, so the landslide is sort of a nexus of like where you have incredibly weak rock. And so what you're speaking to is the strength of the rock, which is a big part of it, the sort of engineering properties of the material. So that's why in the state of California, when we make these landslide susceptibility maps, I sort of glossed over Southern California because Southern California is a little different than Northern California. We have a lot of really crappy rocks that are hosting landslides in Southern California that are not Franciscan melange, but in some respects behave in the same way. And in many cases, it's rocks just like you described. These are things that are very young. Yesterday they were in the ocean and now they've been uplifted and are like barely a rock sitting on the coastline. And so they often have very, very low strength. Whether it's related specifically to the oysters, I couldn't comment on. But I would say that there's plenty of places along the coast that fit that description.
Thank you.
Roger has another question.
Okay, thanks. I was reminded of the vegetation in the pygmy forest up in Mendocino.
Yeah.
Wondering if that's related to your comments about the vegetative covering of these areas.
I think that's a nutrient story that's different. Yeah, I don't remember. I have been there, but I don't remember that those aren't the right rocks. Those pygmy forests form on different rocks. Well, actually, you know what? I'm not sure. I'm not going to comment on that because I don't know, but I'll go read about it when I get. But I think there's something more related to nutrient availability that explains those pygmy forests. It's not a water thing.
Sarah?
I have a really easy one. If I spell PIEZO meter,
Yeah.
could you pronounce it and explain a little more what it does?
Sorry, I put some jargon in there. A piezometer is how you say that.
Oh, piezometer.
And it's just a tube that you insert in the ground that enables you to measure the water pressure.
Okay, so it's not named after, Giorgio Piazza or anything.
And it's different from a well.
Okay.
It would be like if you took a PVC pipe and perforated it just one spot, and then you and you punched it in the ground, and then the water level would rise up within that tube, and it would rise in proportion to the water pressure at that one spot that you punched the hole in. So that's the main way that we measure water pressure in the ground.
Thank you.
Roger?
So another sort of off the wall question related to the deep sea trench that's off of Monterey.
Oh, yeah, I was just thinking about this. Yeah, okay.
Yeah, I've heard that there are landslides down there.
Yes.
And the soil is always saturated because it's under the ocean.
Yes.
So your saturation model isn't going to have any effect down there, correct? Well, so what is causing that?
Okay, well, I sweep some stuff under the rug. Okay, so when we talk about water pressure, it's not actually water. So water pressure in the ocean is what we call hydrostatic, which means that it has the same pressure in every orientation. Okay, that water pressure doesn't matter from a landslide perspective, and we know this because the angle of repose is the same underwater as it is on land. Okay, so water pressure by itself doesn't actually matter from a slope stability perspective. What matters is water pressure that's induced by groundwater motion, which produces non-hydrostatic conditions, and which is to say it produces net forces in the ground that are related to the motion of the water itself. So the case of undersea landslides is even a little bit more complicated because what happens is that often they form in environments where the sediment is being deposited at a rate that the water pressure exceeds that hydrostatic condition due to the rapid burial of sediment. So this is not the Monterey Canyon example, but you can get water pressures that are higher than what you would predict based on how deep you are in the ocean when you're burying something very quickly underwater. So that's one way that we get underwater landslides. Another way is in Monterey Canyon, the mechanisms that are producing slope failures there is actually a thing called a turbidity current. And that's where you mobilize some sediment at the shelf and you get sort of a cloudy, dilute suspension of sand and mud in the water that's a little bit denser than the water is. And it then, because of buoyancy, will tend to collapse and accelerate and produce something that looks a lot like a powder snow avalanche on land, but underwater and with mud instead of snow. And that's the thing that is rocketing down Monterey Canyon periodically. We think about once every 3 weeks there's one of these events. And that's probably that's probably the process that carves the canyon. But slope failures that are triggered on the slope can then turn into these turbidity currents. But the undersea world is a little bit of a different place from a slope stability perspective. There's a lot of exotic things that happen that are a little bit different from on land.
Okay, thanks.
Sorry, Joe, go ahead.
I'll let Sarah go first. Go ahead, Sarah.
Okay. This is really esoteric, but there's a book called Angle of Repose by Wallace Stegner.
One of my favorite
use that
novels.
you use that expression, where this family migrates across the country to Colorado.
Yes, indeed.
But is that also a geologic term? The angle of repose?
Yep. It is. It comes, I mean, it is the, I will say, I don't know if I want to say this in front of the whole group, but that novel is one of my favorite novels, but it was recently discovered that it was largely plagiarized. So the central character of Angle of Repose, Stegner borrowed a lot of her notes in a way that was, you should read about it. It's fascinating because it's one of my favorite novels. It's also set in Santa Cruz and San Jose, where I live. So it's very near and dear to my heart, that book. But yeah, the angle of repose is basically when you have dry materials, the angle that you can hold them against gravity at. And it's typically 30 to 35 degrees for most materials.
Okay. Thank you. That's great.
Joe?
What's going to happen in the next 10, 20 years in this science area of predicting when the next landslide's going to be? We know about the slowing stuff, but is there some frontier that people?
Yeah. To me, it's a great question. I think to me, what's exciting that's happening right now is, especially for its weather, is our understanding weather. What we are now understanding is that it's not atmospheric rivers themselves. It's that embedded in these atmospheric river storms, there are these sort of convective instabilities. They're called narrow cold frontal rain band. They're these very thin things that you see in weather radar that produce incredibly high rain rates. And where they are present often are areas of intense landslide activity during these atmospheric river events. So I would say just from a purely mitigating perspective, our ability to better image weather through radar is probably the best, the place where we'll probably see the most bang for a buck, I think, in terms of that, because ultimately it's a probabilistic thing, and the most important control that we often don't really have a good handle on because of mountains and where the locations of the radars are and things like that is just what was the weather actually doing in a remote location.
Thank you.
Edna?
Yes. Hi, Noah.
Hi, Edna. Nice to see you.
Thank you. I'm curious about the Mission Peak slide, which is enormous. And you can see it, from the freeway. And yet the local architecture committees appear to be ignoring it because the land in that area continues to move. The freeway gets bumpy because of the land motion. And is there...
So, go ahead. Sorry, I'm finishing your question.
Is there any civic restrictions on building on this kind of property?
I mean, I think, first of all, for those of you that don't know, if you're driving down 880 in the East Bay towards San Jose, the highest peak, Mission Peak, has this huge landslide on it. And it's prehistoric, so we don't know when it happened, but Edna, I would just say, sorry, I have a student who's working there right now, mapping, and I've just been out there recently. So that place is fascinating, and despite the fact that it's in the backyard of all these universities, virtually nobody has spent any time looking at that landslide, and it's really an interesting spot. So the restrictions that I'm aware of are really just sort of the standard, ones that would govern, residential and commercial property. And if there's a known landslide there, you can't build on it. MC Hammer's house is the highest house on the hill below that. His former house, MC Hammer lived at the top of the hill. And in 1998, which was a very, very wet winter, the deposit from that landslide was moving and nearly wrecked his house. And you can still see the house there today. So it does periodically move. And we don't know much about what's going on with that thing, but maybe offline, Edna, I'd be happy to talk to you more about it because it's a fascinating but somewhat involved story with that landslide that I'm super interested in.
Yeah, and there was in the time that I've lived in San Jose, because I moved here in 1977, not too long after we moved here, maybe within the first 4 or 5 years, there was a
1982.
Yeah, there was a slide on Sierra Road and a whole bunch of houses got condemned.
Yep.
And the plumbing popped out of the ground and everything else. And my thought was, why did the county let anyone build there at all?
Well, often we don't know. I mean, like a lot of the dams that were constructed in California were built in retrospectively in terrible places, but in many cases we didn't know.
Okay.
And I think a lot, and 1982 is a really important year in California because that's the wet year of record. And people learned a lot in 1982 because it was an incredibly wet 1982, 1998 are the kind of really important years in California history from a landslide perspective because they were so wet. And so, it's totally plausible that things were built in places that were completely stable. And then 1982 came along and, there are many catastrophic landslides that winter. Santa Cruz in the San Lorenzo Valley in Ben Lomond, there was a Love Creek landslide which killed 12 people that winter, which is another big landslide tragedy that happened that same winter. Dick.
Do we have any other questions?
I think, yes, there's one coming. Oh, Dick, you're still muted.
Okay.
There you
So you basically said where, why, when, etc. So what do you perceive is the value of your work to the agencies or whatever that provide the funding?
Yeah, it's a great, I thank you for that question. So I get funding from the National Science Foundation principally, and that means that like I'm working on fundamental processes. And so the truth be told, the area that I interact the most with are people who think about earthquakes, because these landslides are a natural laboratory where we can understand friction in an environment that in some sense is similar to what's happening on faults, but where we can actually make measurements. So, so the people that actually are most interested in the work that I'm doing right now are really people who are thinking about earthquake hazard and what governs the nature of friction on faults, which is kind of a fundamental question in understanding earthquakes. The people who are engaged in mitigation with landslides in the state of California are, like I alluded to, are largely in a reactive mode. So I'm still sort of working on making that bridge to the state agencies to try to, and in particular Caltrans, which is the transportation agency, to try to provide a perspective that is a little bit more forward looking, which is to say, like, here's the where and the when that you might anticipate. But their job is so difficult that it is unsurprising to me that they're less interested in this, just because again they're called in when the road falls into the ocean, and at that point they have other concerns. So I would say, again, to answer your question, mainly it's actually people who think about earthquakes that my work is really, I think, helping to push the science forward. And in particular, the really big earthquakes, the magnitude 9 earthquakes that produce devastating tsunamis. What happens at the very toe of those kinds of earthquakes, that environment is very similar to where we work on these landslides. And understanding how stress accumulates and gets released in those environments is a hard thing to know, because these are often under many kilometers of ocean. And so the observations we're making in landslides can help provide a way for scientists who think about these problems to test their models.
Noah, you mentioned very quickly towards the beginning of your presentation of someone else who might be of interest in the presentation. Would you mind sending me his or her name and email address, and may I drop your name when I contact you?
You will. I'll give you a couple, because if you've never, Bill Dietrich, who is the geomorphologist at UC Berkeley, is the other person. I'll send you an email, Joe, with that.
Yes, thank you.
He'd be lovely to have as well.
Yeah, thank you. Any other questions before we close this? I'm looking at the screen here. Hillary, do you see anyone?
Nothing in the chat. No hands that I can see.
Well then, Noah, let me thank you very much for your presentation, taking the time. I know you're very busy, and bravo.
Thank you. I really appreciate it. This is really fun for me. So I really appreciate the great questions. So thank you.
Okay,
Thank you.
very much.
Thank
We'll see
you
you
a lot,
next month.
Noah. Yeah.